the meantime. So you can really see this impact. So that is an introduction about the theory or the expectation behind this. And now we get to the part, yeah, how can we measure all this? So how can we measure all these phenomena? And for this, we have to really combine instruments because simple reason of the scale of availability of droplets I've shown before. We talk about many small particles, less than a micron. They talk about rain particles, a few of a millimeter. And this range of scales of particle sizes in the atmosphere is calling also for a range of wavelengths that you need to observe those particles. So I can skip this. I can briefly, because I've also shown this picture last Tuesday, but I will show it again and briefly explain what you see here. Because on the left panel, we can see a LiDAR measurement with a wavelength of 1 micrometer. And this is a radar observation of a rain cloud with a wavelength of 10 centimeters. And you can see they're completely different because the LiDAR measurement of 1 micrometer is picking up particles or reflections by particles of much smaller size in the order of micrometers. Then the wavelength of the radar, 10 centimeters, much more sensitive to particles of the order of millimeters. And you can see that the radar is not seeing what the LiDAR is seeing, and the LiDAR is not seeing what the radar is seeing. By combining those two, you can learn much more about the atmosphere. For the clouds observations and cloud and aerosols, you need even more instruments. Right? In the ideal case, you look at satellite observations, because satellite observation gives you the large coverage of the whole cloud field from above. That gives you the spatial component. But it doesn't give you the vertical structure, because a satellite observation only gives you, in most cases, the optical information from the cloud top. So how much reflection do you have from above the cloud? It doesn't tell you what's below the cloud top. You can't see it. Right? If you now look at from below with radars and LiDARs, but then you can also look into the clouds. You can also see what's happening inside the clouds. So to understand then what's going on, in most cases, you need a combination of a microwave radiometer, which is only measuring radiation coming from the cloud, and this radiation coming from the cloud is linked to its temperature and to how much water it contains and how much water vapor there is in the atmosphere. Well, then you have the cloud radar. Well, the cloud radar can really penetrate into the cloud and measure vertical profiles of what's happening inside the clouds. Well, the LiDAR, right, is very sensitive to small particles and also gives you vertical profiles. A pyranometer, which gives us the radiation coming from the atmosphere, and radiosomes, which is giving us a temperature profile, usually up to the tropopause, because the balloon itself will ascend until it explodes. Well, let me show you a case study. So how can you do this type of analysis? And so, for instance, if you look at this cloud deck over here, we can ask ourselves, well, what do we need to know about this cloud for use of improving climate models and weather models? But mostly come down to, we need to know how thick clouds are. So we want to measure this. We need to know how much liquid water we have in the cloud. That's important to know. We need to know how big the particles are. We need to know the number concentration, so how many particles do we have? And we need to know the vertical profile. So how are these quantities distributed as a function of height in the cloud? Well, the general approach for this is that there's no way that you can derive this information from measurements without using an intermediate model. And because you always need a physical model of the cloud in this case, to relate the scattering measured by the instruments to physical properties of the cloud themselves. On this case, as a very simple example, you can have many more advanced examples. We say, well, the cloud itself is a layer like this with a certain thickness, h. We also know from theory that in the ideal cloud, number concentration is constant as function of height throughout the cloud. And we also know from theory that the liquid water content increases linearly with height throughout the cloud. Well, if you know this, if you make this simple model, which is really simple, the reality is a bit more complicated, you can also expect or make an expectation of what you can see with radar and LiDAR. This blue line is the expected response of a radar. And you might recognize, maybe you remember from last time, if you look at reflection by radar, this was related to d to the sixth, right? Diameter to the sixth power. So basically, it's linked to the liquid water content squared. And liquid water content is d to the third. So if you have a linear increase of the water content, you can qualitatively expect a non-linear increase like this coming from the radar. Right? The LiDAR, that's the line over here. Well, the LiDAR, so the short wavelength, will get a strong reflection from below, but the moment the light penetrates deeper into the cloud, it will be absorbed. So you can expect that the signal from the LiDAR will decrease if you go through the clouds. So qualitatively, you can see, well, if this is my typical cloud, then this would be my typical observation with the radar and the LiDAR. Well, this is an example of a measurement. It's not the most exciting measurement. If you look at the cloud deck, a stratocumulus cloud deck, it's usually, well, it's a gray overcast day. So you look up and it's a bit boring weather outside. In this case, it's a few hours that we have this cloud deck at 1 kilometer height. But first, you see that from the below, the reflection is yellow, so it's a very low reflection. And if you go towards the cloud top, well, it turns to red, so the reflection increases, which is consistent with the theoretical model we expected, right? From the cloud base to the cloud top, the radar reflection increases. In this panel here, is the amount of water, so the liquid water path, coming from the microwave radiometer. And you can also see it varies a bit between 150 grams per square meter, around 100, or sometimes very low, around 50 grams per square meter. Now, this is the type of information that you can retrieve from this combination of instruments. The LiDAR here gives you the cloud base, and the radar gives you the cloud top. So we can derive the cloud thickness, the cloud height, liquid water content, and cloud reflection. Well, this can be used together in the cloud model, and then you can try to retrieve things like number concentration and particle sizes. I have a typical study case here, and it's done with measurements from the Azores. So we had instruments put on the Azore Islands in the Atlantic Ocean, and here we can see the radar reflection. Here we can see that the middle panel, what the LiDAR was seeing. So reflection up to the cloud base, up to the cloud itself, and then nothing from below because of the absorption of the clouds. And here we can see the liquid water path. So how much water did we have inside the cloud itself? Well, this has then been used to estimate the cloud microphysical properties. And this is what you get. So in this cloud, you can see, well, the retrieved liquid water content. So low, blue, right? So low liquid water content from the cloud base. And if you go to the cloud top, you can see the cloud water content increases. And that makes sense because if you look at a cloud itself, well, if you start from the cloud base and the volume of cloud droplets moves upwards, yeah, it can collect more water vapor on the way up to the cloud top, and then the particles getting bigger, and you get more liquid water content. So that's the process that you see over here, as seen from the radar and combination with the other instruments. Here we have the cloud droplet size. And also here we can see that from the cloud base to the cloud top. Cloud base, you start with small droplets, and they grow while they are ascending towards the cloud top. So that's also what you can see over here. And here you can see the cloud droplet number concentration. And on average, you see something like 500 to 700 cloud droplets within a cubic centimeter. And that's a large number, but these are also typical numbers of what you can expect in clouds. How many droplets do we have in there? Then the question now is, because we talked about the link with aerosols, well, if you have this type of information from the cloud radar and the LiDAR and the microradiometer, so you know what's happening inside the clouds, can you also measure the relationship with the aerosols below the clouds? Well, you can expect, of course, that if you have more particles inside the clouds, that you would also have more reflection from the LiDAR, which is measuring reflections by dust below the cloud. So we looked into this, and we have many different, I skipped this, a lot of detail in here. So what we did is we say, well, we looked at the below the cloud base, and we look at the LiDAR signal. So how much reflection does the LiDAR pick up at the laser beam wavelength of 1 micrometer? And how much is this correlated to what we see with the cloud radar in the cloud itself? And do we see a correlation there? Well, that's basically what you see over here. So we have a nice panel here, a liquid water path, horizontal axis, and what we call the ACI, so an index, the correlation coefficient, if you like, between the effective radius in this case for the particle sizes of the cloud themselves and the aerosols below the cloud. You should know that from theory, this ACI term has a maximum of 1/3. And that's the maximum value you can achieve in theory. Well, this is what we get. Well, if you look at it, it doesn't look like a correlation at all, right? It all fluctuates around 0 with, and that's about it. So based on this graph, we said, well, there's no real correlation between aerosols below the clouds and what's happening inside the cloud itself. But then we asked ourselves, yeah, but if you look at this correlation between aerosols below the clouds and cloud droplets in the cloud itself, of course, this whole process of bringing aerosols up and activate into cloud droplets only happens if the wind is moving up. And if the wind is moving down again, you won't expect this. You don't have to expect this. So then luckily, the radar and also the LiDAR has the capacity to measure updrafts and downdrafts separately. So you can measure the vertical winds and you can measure the upward winds and the downward winds. So what happens if you separate those two? Then you get this. If you only look at what's happening in vertical wind upwards, then suddenly for this range of particles with the clouds between 70 and 100 grams per square meter, you suddenly see an increase in the correlation between those two. So apparently, there is a correlation between aerosols from below, so dust particles below the cloud base, and the cloud droplets themselves in the cloud base. But you have to really pinpoint your observations to specific dynamic situations in the cloud itself. That brings me to the end again. Time's going fast. These type of measurements, so integrate different instruments and models and for understanding these phenomena, is really crucial. There's no way you can measure cloud properties or rainfall properties in the atmosphere with one instrument alone. You can, but then you have to make many assumptions about the microphysical structure of rain and of the clouds. So there's only one way of getting this done properly. It's combine different sensors. Radar, LiDAR, and microwave radiometers are really crucial for this. And also for the near future, because we are moving in climate studies and weather studies more and more to high resolution, to the details of this, then the standard models that we've used in all the retrieval schemes, that go from radiation to the physical properties of the atmosphere, have to be refined. We cannot rely on these coarse models anymore. We have to go to more detailed models. That's also something that's really the direction of the future, to combine high resolution observations with high resolution models to get a better understanding of the microphysics of the atmosphere. And with this, I would like this part of the lecture, and I hope you enjoyed it. And if you have any questions, well, please go ahead.
Thank you. We enjoyed the lecture, really. So, colleagues, please, questions. Yes, Alexander, I see you raising your hand. Yeah.
Thank you. I would like to make a couple of questions. The first, my question is, can you recommend some approach how to make data fusion, how to combine the data from different sensors, from radar, LiDAR, maybe some other instrument to make some overall picture more detailed, in details?
Yeah. And then you mean data fusion in the physical sense of how we combine those in algorithms?
I mean, if we have, for example, recorded data from different sensors, how we can combine all those data, for example, temperature, pressure, humidity, reflectivity from the radar, and so on, to, for example, identify some types of clouds.
Oh yeah, that's a complicated question. It's ideally, and that's really a tough job, you would like to store all this data in one common database with common data formats, right? And you should have algorithms that give you the opportunity to select the right data segments for the right timing and the right location to do your retrievals. And that's not easy. But one very nice example of getting this done is again by going to the Actris website. So the European program Actris, where this is all put together. And there's many things you can download from there, the codes and data, and also procedures to get you started if you want to.
Okay, thank you. And I would like also to make a second question. How do you feel about the idea that people can make some active impact to compensate climate changes? For example, seeding clouds with some chemical elements and so on, to increase reflectivity or absorb some gases.
I didn't talk about this, but we are active in this field also. My feeling is that we should be very careful with these technologies because we do not know what the unintended consequences will be of this. But at the same time, we have to do research into this domain. Simply because climate change will really kick in. I mean, it's warming, right? And the world is not doing enough to prevent this warming to happen. So we have to be prepared in 2040, maybe 2050, that time, with technologies to cool the Earth. And this could be then a technique to use to modify clouds to reflect more sunlight. So research is really necessary, but we have to be careful.
Okay, thank you very much.
I saw that Artem raised his hand. Artem, please.
Yeah, thank you. Thank you for the lecture. I'd like to ask you about the, let's say, organizational way of studies, because it's a pretty interdisciplinary approach to combine the work of climatologists, the work of radio engineers, of, I don't know, of data analysts. How is it organized in your research group, for example? Who are the main holders of the process? Engineers or climatologists or meteorologists? I don't know. And it's the first part, and the second part talking about the the new students, or I don't know, PhDs that are going to the studies, where do they come from which field mainly?
Okay, well, that's a good question. The first question about the organization, well, it takes time because you have to learn to understand each other's language, and that's really important. But then what you see is that it's really a combined effort of engineers developing technologies and developing techniques, and climate scientists come up to the questions they need to address and why they need these observations. And in many cases, it's really a joint effort. It depends a bit on the program at hand, who's in the lead. Sometimes it's led by the climate community, sometimes coming from the engineering community. But what you really need are persons who understand both sides, right? Who understands the engineering aspects and understand the scientific aspects coming from the climate scientists. And those people are rare. There's not so many of those. So we really have to educate those, right? So when we talk about educational programs, then we really have to focus there. So people can combine physical sciences with engineering sciences, because there are not enough of those people. And in our department, there's also what you asked, right? It is also a combination. We have engineering people looking more into the radar and retrievals of drop site distributions, rainfall rates coming from the radar. And there's a strong component of understanding scattering. That's more like from the engineering side. But we also have people coming from the atmospheric modeling side. They're doing all sorts of models, but then translate these modeling questions into ideas for measurement campaigns, for the validation of the models. And then the two come together.
Thank you. And you have a specific master program, for example, or it's just a research PhD program?
No, there's a master's program called Geoscience and Remote Sensing in the university, and that's aiming at this particular aspect.
Thank you.
Okay, colleagues, more questions, please.
Yes,
Can I ask a question?
Yes, sure.
One question to you, Sinitsyn from electronics department. Do you have the general computer model of the climate situation in the whole country connected with different measurements using these different devices? Or it's as a decision for the climate situation in the whole country, for example, in the Netherlands, using your system?
Yeah, there's a climate model. So the meteorological office in the Netherlands, they run the climate models, not only for the Netherlands, but for the whole region. So also Northwestern Europe. But this model is there. And of course, they use observations sometimes for the validation, the model, for every now and then validation campaigns, and sometimes for initialization. Because you need a start observation to run, for instance, for a small scale forecast of this. So this is there. And what you see is that not only are there observations that we use from the ground part of this, but also satellite observations are used for the validation studies of the climate model. So that's there.
Thank you.
And I ask you one question. Sibruk from the electronic department. At first, I want to thank you for your energy and time which you invested. Very good lecture. And about the question, can you tell us about the practical implementation of your ideas? Maybe in some network of the measurement devices and so on. You see? Thank you.
Yeah, that's a really has been a long time effort to get this done. But the practical implementation itself comes down. This is the measurements we do in the Netherlands. It's a national enterprise where many different institutes collaborate. So it's not just one university with all the instruments. Different universities have different instruments, and we have put them together in one location. And because we all see that it's better to have them together in one location because you get more information out of this than have them separate. And this, of course, comes with many technical implementations about the technical hardware that you need for this, but also a common database, setting up a joint database where you can put your data in the database and everybody has access to this database. So that's also a big part of this. So not only by putting the instruments in one dedicated location or more dedicated locations, but also organize your data flows to the same repository of data and coming up with good disciplines and routines for metadata. So how do you organize your data in such a way that everybody has access to this? And then you have to organize it on the technical level. You make all sorts of agreements on accuracy, on scanning strategies. Well, those type of arrangements have to be made. You have to make arrangements, and it's also done, on how you use the instruments for campaigns, specific campaigns, and when you use those instruments for monitoring, so long-term observations of the same properties to see how much this changes over time. So there's a lot of coordination work involved also in this, and for this you need a good governance structure to make sure that decisions are made at the right location at the right time. So but to get this, to make this happen, it takes years, many years. It's not something you can do in a weekend.
Thank you. And maybe a few words about the sources of investments for this investigation and this process.
The process or the cost, you mean? How much it has cost, the investment cost for this?
No, the question, I guess, about the funding. From which?
Funding itself, yeah. Now, the funding is coming from many different sources. There's a basic funding coming from the governmental sources and to make sure that the basic infrastructure is there. There's also funding coming from the European Union for all sorts of projects, and there's funding coming from the industry for specific projects. So it's a diverse set of funding schemes here. It's not just one funder.
Thank you.
Okay, thank you. And I have further question regarding this as well. And do you have some Horizon Europe projects or Horizon 2020?
Now, like I said, what the main driver for on the European level here is the ACTRIS program. And ACTRIS is ACTRIS. That's European program supporting atmospheric infrastructures. That's European activity. And on top of this, we also have more European programs like program called Urban, which is looking into atmospheric situations in urban areas. So with campaigns and observations in there. There are European programs for the combination of these observations and viral outbreaks to prepare ourselves for the next pandemic, which you can expect if the Earth is getting warmer, we will also get changing patterns of mosquitoes, for instance. So we want to understand this relationship better between small-scale weather patterns and the changing patterns of biodiversity. So we have several European programs in place for this.
Okay, thank you very much. Professor Janowski raised his hand.
Yeah, I wanted to ask a question. First of all, I would like to thank Herman very much for brilliant series of lectures. It was really very interesting, and I can see that your lectures caused great interest in our audience. And we could see that there are great efforts, intellectual efforts and financial efforts and organizational efforts to this field, to this research and investigations. And I would like to ask What do you expect? Are you going really to improve the situation with climate action, or maybe you have already achieved some practical results in this purpose? Such a strange
yeah.
question.
So when it comes to climate action, I think the work that I've shown here will have a huge impact on, well, directly on, for instance, climate action in urban areas. Because if you look at urban areas, so the large metropoles across the globe, we need a much better understanding of heat stress, so heat in the city, and how we can accommodate this heat in the city. But for these type of observations and the models coming out of these observations are really important. And so there it will help. The same is true for what we call sponge cities. So how does a city, so large city, deal with extreme rainfall? So how can you, so you need models and observations, and certainly good models based on observations, to plan clever adaptation technologies in urban areas to deal with the extreme rainfall that we can expect. But these are two examples of how this can link to climate action. The same as how it can link to climate action is a much better forecast of extreme rainfall. As we can now see with extreme rainfall, the storms, they come, they develop very fast, and they are very difficult to predict the day ahead. But the more accurate these models become, the forecast of these systems will also become more accurate. That's another example of how this can contribute to climate action. And of course, the longer term observations coming from measurements like this will also give us more information about expected droughts, for instance, right? So how can you get a long period of absence of rain? And what will the impact of this be? Because the surface dries out, this will amplify the heat itself over land. So how are these processes then propagating over larger areas? All this type of information is important for climate action. And then I'm forgetting on another 10 examples. There are many more.
Yeah. Thank you very much.
Okay, colleagues, any other questions?
Maybe
Yes,
one
can I ask?
question, extra question. Can you predict a future of the climate in our planet? Is it good or is it bad for all of us?
Prediction of climate, the future hard to predict, right? But I can give you my feeling for what I expect. And my expectation is that no, we're not doing enough to keep the global warming within acceptable limits. So I think we are heading by the mid this century, maybe the end of this century, to something like 2.5 degrees of warming, and which is a huge amount of warming. And so whether this is good or bad, that will depend on the person itself. But in many cases, this is bad news, because it will lead to more extremes. And these extremes can go either way. They can go to more droughts, so long dry periods, and they can go to long wet periods. So my own gut feeling is not so positive. But it's not a prediction, that's more my intuition and my expert intuition, put it like this.
Have you the mathematical model of these climate changes?
There are plenty of models about climate models, there are very good ones around. But the difficulty with using those for the future is that it's very hard to predict how politicians will act. And that's because because you need information about the CO2 emissions for the future, right? But that's a very important element of how the temperature will develop. And so we know that the physics is easier to understand and predict than human behavior. And that's the hard one.
Thank you.
Please. Any
Yes,
other
can I
questions?
ask?
Yes, sure, Anastasia.
First of all, I want to thank you for very interesting and meaningful lecture.
Sorry, Professor Ulansky, you will be the next. So please, Anastasia, go ahead. Sorry for
Yes,
interrupting.
my question in some way connected with previous. Can historical or previous cloud data that received from radars imagery be utilized to predict climate changes, and maybe a correlation has been identified between long-term cloud observation and some climate trends? Thank you.
Of course, that's a good question. I think that historical data is very important because certainly of a phenomenon like clouds and so on, because they can be used to validate the quality of the model. Right? Because if you have historical data, you can also test then how good a model is in reconstructing the past. And it gives you more confidence in the physics of the model. And then it will also give you more confidence in the forecast made by the model. But it's very important information. If you have historical information, you really need it.
Thank you. And another one is connected with human activities. I mean, do human activities, for example, like industrial emission, have a huge impact on the formation and the structure of clouds, and as a result, climate changes? And can this be monitored in some way?
Yes, well, there are plenty of examples of how you can see the impact of the industry on the clouds themselves. And you can see this in satellite images. You can see that the moment a cloud field passes over industrial areas or over the sea, when you have cargo ships sailing underneath the cloud deck, you can see a change in the cloud. So, for instance, more particles of smaller size. And that's there. So the industry is really affecting the clouds.
Thank you.
Okay, any other questions? Professor Ulansky, please go ahead.
Yes, thank you for this very interesting lecture. My question is related to the past. Is it possible using developed mathematical models to estimate the state of the atmosphere in the past, say 5,000 years ago, 10,000 years ago, and compare with the state of the atmosphere now to understand what are the changes and the reasons of these changes? Thank you.
Yeah, many models have done this already to reconstruct the past, partly based on observations. And most of these observations are geological observations. The further you go into the past, the more and more you get these observations based on drilling holes in the surface and collecting ice cores, for instance. Or you look at tree rings for this. But these are all indirect observations. We have not so many direct observations of the atmosphere. The direct observations of the atmosphere only started around the end of the 18th century up to now. So the past has really been reconstructed based on indirect observations. And of course, models have been constructed to put those informations or observations into the right context. So that's there, the information.
Thank you.
Okay. Who else? I have one question from my side. As you know, in National Aviation University, we are all working a lot with unmanned aerial vehicles. So you used in your research ground stations, also some observations from the satellites, but can we use, for example, to fly inside the cloud and to measure with preset up lidars, radars, and other equipment on the UAVs, for example, these characteristics, properties of a clouds?
Yes, you can. I didn't mention it, but yes, you can. It's really an upcoming field to use UAVs and smaller drones to do atmospheric measurements. The problem we have with this in the Netherlands is regulations. We cannot go that high with drones, but in principle you can. So that's really an upcoming field to use UAVs and drones for atmospheric studies. And in Europe, the leading institute for this is the Cyprus Institute on the island of Cyprus. Because they have more free airspace and they can do experiments and flights and tests with UAVs to do these measurements. But unfortunately, they don't have many clouds over there. They mostly measure aerosols and dust particles. But it's really an upcoming field. It's a very important part.
Okay. Okay, thank you. I think that we can contribute there as well. So
Yeah,
with our experience, once war will be finished, we will have a lot of drones which we will use for different purposes. Okay, colleagues, any other questions? Okay, I think that the time is gone. So thank you very much again, dear Professor Russchenberg. It was a great pleasure to meet you, to discuss these issues, climate changes with you. So we received a lot of relevant, important, and very helpful information for us. And I hope that in the future we will find a way how to collaborate together. So we have a lot of experts. Today we have more than, I guess, 10 professors from different departments of our university. And they are highly experienced in different areas, in electronics, in radar systems, in environmental changes, and so forth. So let's try to find a way how to collaborate in the future. And thank you for this amazing series of lectures.
Thank you very much. It was my pleasure. I really enjoyed doing it. I really hope that the war ends soon, right, for you. I really hope this.
We hope so as well.
Okay. Okay.
So thank you. We can
Thank you very
close
much.
the session. Thank you all, and happy Constitutional Day of Ukraine to all of the participants.
Okay. Thank you. Bye-bye.
Goodbye.